So as we pick back up in this 12.5, we're talking about expected payoffs. So we just worked through this example talking about for the charity, expected payoff for the charity, expected payoff for the person making the donation. So when we talk about expected payoff, the average the charity can expect to make, or the average the person could expect to win, those type of things. So we had another example here about Margaret. Margaret has $10 to spend on game tickets for a charity fundraiser. Which game should she play to create a greater expected payoff for the charity? Okay, so we are looking here a greater expected payoff for the charity. Okay, so you always have to pay attention to that because sometimes they're asking about the charity, sometimes they're asking about you as the donor, the person, playing the games or whatever. So here we have two games. In game A, a ticket costs $5. There's a $2,000 prize, and your chance of winning that prize is 0.001, or in other words, 1/10,000. Okay. In game B, a ticket costs $10. $50,000 prize can be won, but your chance of winning that prize is 1/10,000, so 0.0001. And keep in mind that Margaret has $10 to spend, right? So my suggestion is that we look at each individual game. What about game A? Okay, if we're going to find the expected payoff, the expected value. For game A, you're always going to be paying $5 for the ticket, right? And then you might be winning the prize of $2,000. Your chance of winning that prize is the 0.001. Now remember, when we were doing our expected values yesterday, it was always the outcome times the probability. So your chance of winning that prize, your chance of getting that money is 0.001 of that money value. Now, we want to look at this from the eyes of the charity, yes? Ticket cost is $5. When I pay that $5, they are bringing in $5, yes? Okay. What about that prize? If I win that prize, what's happening? I'm getting $2,000, but what's happening to the charity? They're losing $10,000, yes? Or $2,000, excuse me. So as we think about this, again, we're trying to look at the payoff for the charity. Anyone that plays game A, or I guess it's Margaret here, they're going to get $5 from Margaret if she plays the game. Plus, now, if they have to pay out the prize, that prize is a negative for the charity, yes? What's the chances they have to pay out that prize? And that is the 0.001. So that expression represents the payoff for the charity. The charity is going to gain $5, and they have a 1/100th chance of losing $2,000. Do the math. 1/1000th of 2,000, or in other words, 2,000 divided by 1,000 is just going to be 2. But 5 plus -2 is going to be 3. Are you with me there? Okay, so I pay $5. I only have that 1/1000th of a chance, so that's represented by the -2. So they're still bringing in $3. Okay, evaluate game B with the same idea. What do we know about game B? The charity's definitely going to make how much? $10 every time that Margaret plays the game. Plus, what else do we know? The charity could be paying out $50,000, and if the charity has to pay that $50,000 out, that's going to be a negative $50,000. What's the chances they pay out that $50,000? 0.0001, 1/10,000. So what's going to happen here? We're going to have the 10. 1/10,000th of 50,000 is going to be -5. So 10 minus 5 is going to be $5. Okay. Here's the big question. Which game should she play to create the greater expected payoff for the charity? I'm disagreeing. What's the key we have to go back and take into account?
Margaret has like 12. So they make 6.
Slight catch here, yes.
Yeah.
Katie's not impressed with the catch. Okay. Now, here's the deal. If we're just looking at playing game A once or playing game B once, if we just play each game once, then game B has the greater payoff for the charity, yes? What's the catch? Margaret has said, I am spending $10. Would it be better for the charity for her to spend $10 by playing game A twice or playing game B once? Game A twice, because that expected payoff for the charity is $6. Do you see that point there? Little detail, that's the thing. There's a lot of pieces you have to look out for here. So I'm going to kind of write the information out so you can see it and understand why. But game A, Margaret's spending $10. $10 will buy 2 tickets, and that means the payout for 2 tickets is going to be $6. As opposed to game B. In game B, $10 buys 1 ticket, and the payoff for 1 ticket is $5. With that in mind, can you agree game A is going to be better for the charity? And it's only because she's spending specifically $10. Okay? Watch all those little details. I mean, my brain, that's what's hard about these type of lessons, is because there's so many little details you have to take into account. Okay? But the idea here, take whatever solid piece of information you know, add or subtract it to the probability of the other unknown piece. Okay? We know we're paying this ticket cost. The unknown piece is the prize. So we're using the probability of that prize. Okay? Questions there? Okay. In this next section, we're going to use expected value, so the same idea, to evaluate strategies. So both of these are situations where kind of what's the better deal. Okay. This first one is car insurance. The other one is dental insurance. So you're considering options for an auto insurance policy. The insurance company offers new car replacement insurance in the case your car is totaled. There is a 1% annual chance of the car being totaled. Which of the two plans has the lower expected cost? Okay, so again, when we talk about that lower expected cost, it's kind of the idea of the average cost. Now, in your chart, you see that Plan A has a premium of $50, a deductible of $500. Plan B has a premium of $60 and a deductible of $0. Now, do we understand the vocabulary in this question? Do we know what a premium is? Do we know what a deductible is? You're hitting that age where you need to. Okay, and I'll say that because you guys are drivers or soon to be drivers, right? At some point, you'll have to have your own insurance. You know. So, okay, so a premium is that set amount that you or most likely your parents pay each month or each however often they pay it, okay? And I don't know, these premiums are kind of cheap. I don't know, they're monthly maybe. Even then I'm thinking that seems kind of cheap, but I never pay just one car. So, but okay, so the premium, you pay that amount each month to have the insurance. That's what the premium is. The deductible is, okay, I have to file a claim. Okay, so this is car insurance. I have to file a claim to get my car repaired or whatever. The deductible is the amount that I have to pay out first before insurance starts paying. So with this one, I have a $500 deductible. So that means I have to pay the $500 base deductible. And then past that, the insurance company is going to cover my repair. That's the benefit of me having insurance, is the insurance company covers that repair, or in this case, we're talking about replacing the car. Okay. In this plan, premium is $60, so you pay that $60 each month. But with this higher premium, this one has a $0 deductible, which means I file a claim to get my car repaired, I don't have to pay anything because I pay my monthly premium. Does that make a little bit more sense of premium versus deductible? Okay. I really like this example. It's really appropriate at high school level, but it doesn't make sense if you don't understand the vocabulary. So, let's look at Plan A. Okay, let's find the expected cost here. So what do we know for sure about Plan A? You for sure are paying that premium, right? That is your known cost. And so we're going to pay the $50. Plus the deductible. That's our unknown, right? Because that, are we going to need to use our insurance? So what are the chances of us paying that deductible? There is a 1% annual chance of totaling a car. Okay, according to this insurance company at least. So what's that mean? If I total my car need to get replaced, I'm paying my deductible, there's a 1% chance. So what am I going to do with the 500? 500 is going to be multiplied by the 1%, or the 0.01. So this is basically an average cost of what? 1% of 500 is going to be 5. And 50 plus 5 is 55. So this is the expected cost, the average expectation. Obviously, if you have to use it, you're going to be paying the whole thing, right? But this is using the probability behind it that there's only 1% chance you're likely to use it. What about Plan B? The known that I'm definitely paying is $60. Plus, if I have to get my car replaced, what am I doing? You're not paying anything, right? I mean, if you want the official math, it is 1% of 0. And so that's just going to be $60. So which of these two plans has the lower cost? And that's Plan A. Which basically supports the idea that they're saying there's only 1% chance you're going to total your car and need to replace it. And so, since there's only a 1% chance, the better deal, so to speak, is Plan A, where you have a lower premium, but if you have to replace your car, you have that deductible. And here the option is car replacement. This also works for if you're getting a repair under your insurance. Okay. Questions there? Here's the deal, guys. That's how car insurance works. Health insurance has some similar things, okay? Your parents pay so much a month for health insurance, okay? Now, there's a little bit more that goes into health insurance, but generally then your parents have a certain deductible where they have to pay everything up to a certain amount, and then insurance covers more after that amount. Okay, so you have a deductible again. In this case, Zach has two choices for dental insurance. Both cover routine expenses. So your basic cleanings and that type of stuff. He estimates there is a 25% chance he will need a crown that's going to cost $1,500. And he is expecting no other non-routine expenses during the year. Which insurer has the lesser expected total cost? Okay. Now, there's a slight catch on this one we have to consider. Let's look at each of these. Let's look at Dentifix. Okay. What do we know about Dentifix? We're paying $600, right? That is our known guaranteed cost. Plus. Maybe he gets the crown fixed, maybe he doesn't. Yes? So what do we have to consider with the crown? Just the opposite.
He would have to pay everything.
He would have to pay everything on the crown because $1,500 is before $1,800. Okay, so he would, and keep in mind we're going to use the probability that there's only a 25% chance, but the idea is if he has to get that crown fixed, he's paying all $1,500 plus the next $300 of dental expenses he has before dental insurance starts covering it all. Okay? And I'll be honest, in health insurance, there's often a lot of percentages. They say, okay, you cover it all up into this point, and then past your deductible, okay, we're going to cover maybe 90 or 80% or something. They won't cover it all, but they cover more. So here's the deal. This deductible is $1,800. Do we have to do 25% of the whole deductible? No, because we're just talking about 25% of his crown, which is $1,500. So in his case, if he only uses that $1,500, it's the $1,500 that we're taking 25% of. So the math you're doing is whatever 25% of $1,500 is, and then adding that to $600. So notice I didn't use the whole deductible because his crown is less than the whole deductible. What are you guys getting? $975. And then we have, I don't know, is this enamel? Enamel? I don't know. Whatever this other company is. Okay. What about this other company? We know he's paying $750, yes. What about past the $750? What'd you say? No. He's only going to pay $700 of his crown. Okay? Because, so, the crown costs $1,500. He has to pay the first $700. And after he pays the first $700, the insurance company will take over and pay the next $800. So for our purposes, though, there's only a 25% chance he's going to need this crown replaced. So we're saying 25% of what? Of the $700. We're using the whole deductible this time because he would need the whole deductible. So it's a $750 plus the $700, the 25% of the $700, and this gives me $925. So, if this is truly how it works, where's his better deal? Enamel? Okay, they have the lesser expected cost there. So that's a situation where actually the little bit higher premium with that lower deductible is actually the better deal. Okay. You're seeing a trend here, yes? What always looking for that known cost or whatever. We're adding a probability of whatever chance we're looking at there. Now, we have one other topic on the back side here. Okay. And on this, we're talking about using probability to find expected value. Okay? So, according to the weather app on Talicia's smartphone, there is a 40% chance of rain for each of the 5 days of her vacation. How many rainy days should Talicia expect during her vacation? Okay, so thinking ahead about expected value, remember, expected value is the outcome times the probability it's likely to happen, plus the outcome times the probability it's likely to happen. Over and over and over, yes? Now, it's 40% chance of rain for each of the 5 days. What we want to look at, we're using our binomial probability. And if you notice at the bottom of my paper, I have a reminder here, yes? What did we learn last lesson? I think it was last lesson, wasn't it? Did we learn this binomial probability formula? We did. Okay, it's not the smallest thing, but the good news was we had calculators, right? So in order to find the expected value here, we have to find the probability at each day that it's going to rain. So we're doing, probability each day that it's going to rain. So at 0, if it rains no days, if it rains 1 day, 2 days, 3 days, 4 days, 5 days, and then we're multiplying those. So notice I left a lot of workspace here, right? I did that for a reason, because we're using that formula. The idea, and I don't know if you see where I'm going with this, but we need to find the probability of rain 0 days, the probability of rain 1 day, 2 days, 3 days, 4 days, and 5 days before we can even begin to find our expected value. And so when I say find the probability of each of those days, realize that's using this formula. That's using our binomial probability. Because if you remember binomial experiments, there's 2 outcomes. Either it rains or it doesn't rain. The probability of rain each day is the same. And 1 day's rain does not affect the other day's rain. Remember we had those 3 qualifications. Well, that's what we're doing here. So our formula, NCR, P to the R, 1 minus P to the N minus R. Well, what's P? My probability is going to be 40% for 1 day. And what is 40% as a decimal? 0.4. N, the total number of trials. How many days are we talking about here? 5 days. R is the number of days in question. Your R value are going to be those numbers there. We're going to 0, 1, 2, 3, 4, and 5. Okay, so we're setting these formulas up. We'll obviously be able to use the calculator. Remember, it's NCR. So NCR for the first one, 5C0 times P to the R. Well, my P is 0.4, raised to the R is raised to the 0. And then if you recall, 1 minus P. So 1 minus 0.4 raised to the 5 minus 0. Now, I'm not going to clean every one of these up and write these all out, but do realize that 1 minus 0.4, 1 minus 0.4 is always going to be 0.6 as we go down this page, right? And in fact, I'm going to write 0.6 on the future run options. And 5 minus 0 is 5. So I believe 5C0 is 1 if I'm not mistaken. 0.4 to the 0 is going to be 1. So you really are just finding 0.6 to the 5. Did you guys get a value? 0. 0.07776 is what I've written down. Can we get some agreements there? And now we're repeating this process. Probability at 1 day. So now it's 5C1 instead. Instead of 0.4 to the 0, it's 0.4 to the 1. That 1 minus 0.4 is always going to be 0.6. So I'm going to just go ahead and fill this in as 0.6. And now, instead of 5 minus 0, it's going to be 5 minus 1. Or if you prefer, you can just put 4 in there. .2592. Repeat for 2 days. 5C2. 0.4 to the second. And 0.6 to the third, if you will. It's 5 minus 2. I have 0.3456 written down. P of 3, 5C3. That means 0.4 to the third, 0.6 to the second. Can I just go ahead and say that, or is that going to confuse? It's 5 minus 3. And .2304. P of 4, 5C4, 0.4 to the fourth, 0.6 to the 1, .0768. And 5C5, 0.4 to the fifth, 0.6 to the 0. And nope, I remember that totally wrong. 0.01024. Okay, we found all the probabilities, guys. To actually do the work, we have to find the expected value. In this case, it's the expectation of rainy days. How many rainy days should Talisha expect during her vacation? So as we do this, remember it's going to be the outcome times its probability. The outcome times its probability. So at 0 days, the probability is the 0.07776. We're going to multiply those. Plus, at 1 day, we're using 0.2592. So you're multiplying the number times its probability. So as I start writing this out, 0 times 0.07776 plus, then we're going to do 1 times 0.2592 plus, now I'm going to do 2 times 0.3456 plus. I'm going to do 3 times. What am I doing 3 times? 0.2304. Plus 4 times 0.0768. Plus 5 times 0.01024. Now, I don't know if anyone's actually doing the calculator bit on that yet, or if you guys are still writing. I'll be honest, I was kind of surprised at what the answer ended up being. Just because of all these messy decimals, I'm expecting a messy decimal. You don't get one. You get the plain old number of 2.
No, there's a much easier way to do it.
That doesn't use the binomial probability?
No.
How is that?
It's 0.4 times 5.
I don't think that would always work, though.
No.
I don't think that always works. I could be wrong on that. You're just saying 40% of 5.
It was 2.
I agree. I'm not disagreeing with that
I looked at
math.
it and looked at that. I'm like, that's probably gonna be 2. It was 2. Maybe we can pull up another problem and do the same thing then.
Yeah.
Not funny.
I'm have to think. I'm trying to think why it doesn't always, because there's some reason it doesn't always work, but I'm not sure. At the top of my head, I can't pull out what it is. So I think it's a coincidence, but I'm gonna have to look into that now, because now you've got me curious. I see what you're saying. Yeah.
Because when I was first looking at it, I really thought about it. I'm like, that would just be 2, wouldn't it? And it's 2.
I don't know. I have to look into that now.
You can look in favor. First thing I did.
No, I get it. I'm not arguing that. Yeah. Okay, guys. We have one other example here. Now, I will say on this other example, and I'm almost tempted to forego it, this other example is really kind of what we were just doing, just they already kind of filled in some of the numbers. Okay? Can't remember what the other one was. What is this one? A carnival game has 4 orange lights and 1 green light that flash rapidly one at a time in a random order. When a player pushes a button, the game stops, leaving 1 light on. If the light is green, the player wins a prize. Complete the table, then determine the number of prizes that a player can expect to win if the game is played 4 times. Okay, so the idea here is the game is played 4 times. If the light is green, they get a prize. Okay. I don't think they even gave us, or I guess I didn't type it in there, but what you've got here, you've got a 20% chance, because there's 5 lights, okay? So 20% chance of getting 1 light. That means an 80% chance of not getting that 1 light. This is already filled in. They've already done that. The idea here is that it's always 4 times, but this would become 4C1 as we look at the number of green lights. 4C2, 4C3, and 4C4. Realize that second number is your exponent, right? 1, 2, 3, and 4. So those are your exponents on your probability. This next piece that's already filled in, this is your 1 minus the probability. So 1 minus 0.2, which is the 0.8. And then this 4, that is your n minus r. So in this case, it was 4 minus 0. The next one would be 4 minus 1, 4 minus 2, 4 minus 3, and 4 minus 4. Okay? And again, it's filling in the pieces. I'll go ahead and fill in the pieces, but it's the same idea. So 0.4096, 0.1536, 0.0256, 0.0016. When you do your expected value, okay, it's the same thing. Number of chances, number of times we're talking, the probability. For the outcome, probability. So in order to do that, it'd be the 0 times its probability of 0.4096. The 1 times its probability of also 0.4096. The 2 times its probability of 0.1536. The 3 times its probability of 0.0256. And lastly, the 4 times its probability of 0.0016. Okay? You end up with an expected value of winning 8/10 of a prize. Okay? Okay. Your homework that is in Savas is lesson 12.5, of course. 12.4 scores went into Skyward this morning during first hour. So if you didn't have Skyward or 12.4 done, you'll want to get that done. And let me know if you have questions. I will say, this is one of those lessons. It takes the reading, trying to figure out all the pieces, okay? So bring back questions tomorrow if you have them.